In the previous video, we talked about base units, and one of the base units that I mentioned is the mole. Now, the mole is used to calculate substances that are extremely small, like the atom and molecules and ions. The mole is a number. Like when I say dozen, you automatically think of 12. When I say pair, you think of 2. When I say baker's dozen, you think of 13. The mole is just that. It's a number. The number is 6.02 times 10 to the 23 atoms. Now think of that number real quick. Times 10 to the 23. Is that a very large number or a very small number? It's a large number. It's 10 to the 23rd power. So before I really talk about it, I want you to imagine, think about an atom. Can you see an atom? You can't, right? Not with your naked eye. What if I were to give you 6.02 times 10 to the 23 atoms of a substance? Could you see it now? It's probably hard to imagine what that would look like, right? So let's take aluminum for example. If I gave you an atom of aluminum, would you be able to see it? No, you wouldn't. If I gave you 6.02 times 10 to the 23 atoms of aluminum, you could see it. And it looks something like this. This is probably a blown up picture, but it would be a ball of aluminum. It makes it so that scientists are able to work with the substance. We're able to count the atoms, and this is what a mole is. So 6.02 times 10 to the 23 atoms of aluminum is equal to 1 mole of aluminum. Now to explain how big a mole is, I'm going to show you just a clip of this video.
Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank.
Now, hopefully that video gave you an idea of how big the actual number is. So in chemistry, the mole is a unit of measurement. Again, we can't see one atom, right? But when we say 1 mole, we know that we are talking about 6.02 times 10 to the 23 atoms. And this makes it so that it's easy to convert and count atoms, molecules, ions, particles, substances that are extremely small, things that we cannot see with our naked eye. So 1 mole is equal to 6.02 times 10 to the 23 particles. Now that word particles can also mean different things. So it could be 1 mole is equal to 6.02 times 10 to 23 atoms. 1 mole is equal to 6.02 times 10 to 23 molecules. 1 mole is equal to 6.02 times 10 to 23 ions. And 1 mole is equal to 6.02 times 10 to 23 formula units. The whole point is that all of these particles are extremely small. Particles, atoms, molecules, ions, formula units. This number is called Avogadro's number. So when you think of 1 mole of a substance, think of Avogadro's number, 6.02 times 10 to the 23. Now let's use dimensional analysis to help us convert from moles to particles and particles to moles. How many moles are in 1.204 times 10 to the 24 atoms of phosphorus? So what we do first is we set up our fence, and we start with the top left corner of our fence with the number that's given. In this case, it's atoms of phosphorus. And the units are important. Make sure that you are writing the units, like particles, atoms, formula units, and you're also writing the substance with it. So in this case, it's phosphorus. And then what do we do in the fence? What's the next step? We copy down the units. So we have atoms of phosphorus that we bring down to the bottom of the fence. So we write atoms of phosphorus. And think about the conversion factor here. Because remember, the second part of the fence, we write a conversion factor. So what is the conversion factor for all of these problems that we're going to look at today? It is that 1 mole is equal to 6.02 times 10 to the 23 particles, and in this case, it's atoms. Remember that I can write this the other way, where Avogadro's number is on top and the mole is on the bottom. So it's saying 6.02 times 10 to 23 atoms per mole, per 1 mole. So which one are we going to use to put into the bottom of our fence? Right, we're looking for the one where the atom, the word atom, is on the bottom. So we're going to use this one here and put that in the bottom, or in this conversion factor fence. So we write moles on top, and then copy the numbers. Where you see mole, you write 1. Where you see atoms, you write Avogadro's number. Our like units will cancel out. Remember, you multiply across, and then you divide, and you get an answer of 2.000 moles of phosphorus. So this is using significant digits. For all these problems, we're considering significant digits. Now, a couple of things before we move on. You notice that instead of writing MOLE, I wrote MOL. MOL is the abbreviation for mole. Why we just knock off one letter for the abbreviation, I'm not quite sure, but MOL is the abbreviation for mole. Now, if you did not get the answer 2.00, again, make sure in your calculator you are using parentheses around your scientific notation number, and that should help you with that. Okay, so try it again. If you did not get 2.000, use parentheses and calculate your answer again. How many moles are in 2.408 times 10 to 25 formula units of AlF3, aluminum fluoride? So we start in the top left corner of our fence. And there actually is no abbreviation for formula unit. So you do need to write the entire thing. AlF3. We draw our fence. And what do you do next? You copy down the unit and what's going to go on top. Again, formula units can only be equal to one thing, and that is the mole. So we write mole of AlF3. How many moles? 1 mole is equal to 6.02 times 10 to the 23. Like units cancel out. And our answer is 40.00 moles of AlF3. How many molecules of chlorine are equivalent to 3 moles of chlorine? So we start with our given, 3 moles. We copy down the unit, moles of chlorine. And what's going to go on the opposite side? Well, it's giving us moles, and what is it asking for? It's asking for molecules. And mole is not short for molecule. Okay, so think of molecule like a particle. It's an atom, right? Similar to an atom. That's what molecule is. Mole is not. Remember that mole is something that is big enough for us to see and use for experiments. So, what do we put here? How many molecules is equal to how many moles? 6.02 times 10 to the 23 molecules is equal to 1 mole. Our moles cancels out, and you multiply across, you divide by 1, and you get an answer of 1.806 times 10 to the 24. Here we do only want one significant digit, so that goes to 2 times 10 to the 24 molecules of chlorine. By the way, if you're thinking, why just one significant digit? Our conversion factors, we don't consider this when we're thinking about significant digits. So we don't consider literature values that are given to us. We don't consider constants that are given to us. We only consider the data that's given to us. Okay, so we only consider the 3. That's why it's one significant digit. So here we have 5 moles of Na+. We bring down mole of Na+. It wants to know ions. of Na, right? And so we have 6.02 times 10 to the 23 ions is equal to 1 mole. Cancels out. Multiply across, get an answer of 3 times 10 to the 24 ions. Go ahead and try these problems on your own. I do want you to show me the setup. You should have the setup on your paper just to practice dimensional analysis. Remember that this is not going to go away. We are going to continue to use it throughout the year. So go ahead and set it up. Pause the video here. Play the video when you're ready to check your answers. I will go over these problems in class.